Hi everyone, welcome to the exercise class. So today my plan is to discuss two topics that come up in the exercise sheet for this week. So first one has to do with the notion of cooling a qubit and how we can cool a qubit using a virtual qubit, which we extract from a multidimensional system. And the second topic is how we compose virtual qubits. So both of these both of the operations that essentially these two um, topics consist of already been touched in the lecture, but I'll just briefly repeat the procedures so it will become clearer. Yeah, feel free to ask questions and interrupt whenever. So first, let us start with the notion of cooling a qubit, and to kind of get a physical feeling of this operation, let us return to the swapping procedure, which was discussed in the lecture. So the swapping procedure can be applied to two qubits. So both of them can be real or virtual. It doesn't matter. So for example, for two real qubits, this operation would look like as follows. So suppose that we start with two real qubits, which are both in a diagonal state. So PS00S plus 1 minus PS11S. And the second qubit, we'll label it as V, is PV00V plus 1 minus PV11V. And then the composite system, the state of it can be described by just a tensor product of the states of the individual systems. And then the swap operation, what happens is we just exchange between these two states. Let me write it out this way, as in 0s tensor 1v is exchanged with 1s tensor 0v. So this is essentially the swap operation, which as a unitary on a joint system can be written as, so if the system is in a state 0, 0, nothing happens. If the system is in a state 0, 1, it goes to the state 1, 0. If the system is in a state 1, 0, it goes to the state 0, 1. And then if the system is in a state 1, 1, nothing happens. So this is the unitary, which corresponds to this operation. And what happens to the state? Well, we can just see. So we start with the state rho, which is rho s tensor rho v, which can be written as diagonal state ps pv, ps 1 minus pv, pv 1 minus ps, and 1 minus ps 1 minus pv. And all the other terms are 0. Okay, and essentially after we apply the swap operation, the populations of the levels 0, 1, and 1, 0 swap. So they're just exchanged. And we end up with the state rho prime, which is this term stays the same. These two are exchanged as indicated above, and the last one stays the same. And this can be written as a following tensor product on two individual systems. This will be PV00S plus 1 minus PV11S tensor product. Yeah, let me write it on the other line. So this will be PS00V plus 1 minus PS 11V. So essentially what happened is the states of the qubits just exchanged. So the population of the states are exchanged between the qubits S and V. So the populations are swapped for S and V. So the question is now, how can we interpret this thermodynamically? So, and the idea here is as follows. So suppose that you have these two qubits, S and V, and we interpret their diagonal states as some thermal states. So here we have states 0, 1, 0, 1, and the system, and the state of the system S is a thermal state for some temperature T1, and the state of the system V is a thermal state for some temperature T2. And then if we look at the swap operation and apply it to these two qubits, so if we label this also TS and TV, then essentially their populations are swapped, which means that their temperatures are swapped, and we end up with the system S with temperature T2 and system V at temperature T1. And the idea here that if T2 is less than T1, then this operation effectively decreases the temperature of the qubit S. Which is actually called the cooling, as cooling of this qubit S. Of course, if we want to, and then it depends to which state we would want to cool our qubit S. For example, if we want to cool it to the zero temperature, which corresponds to the beta V equaling plus infinity, then we need to take the qubit V, a real qubit V in a state 0, 0. So after the swap operation, system S would end up in a ground state. Okay, this was a situation for two real qubits. Of course, one can also imagine that we would need to carry out such a cooling operation, but where we would only have access to a virtual qubit. So cooling a real qubit with a virtual qubit. And the idea here is that because the virtual qubit is only a subspace, or constitutes only a subspace of a larger system, then we cannot perform the swapping operation as efficiently as if it was a real qubit. So with a real qubit, we can just swap it and end up in the same state as the qubit we were swapping with. But if we swap with a virtual qubit, because there is also some residue from the rest of the subspaces, then we would not get the the state of the virtual qubit exactly. But if we repeat this operation many times, each time resetting the virtual qubit, or you can also see the resetting of the virtual qubit as just using a lot of copies of the virtual qubit, then we can achieve the same result as if we were swapping with the real qubit. So, and here let us take a following example just to maybe demonstrate it. So suppose that our real qubit is initially in the state which is maximally mixed. So it's 1/2 0 0 plus 1/2 1 1. And what we want to do is we want to cool it to the ground state using a virtual qubit. Okay, and analogously with the case with the real qubit, of course, the optimal virtual qubit that we have to choose to cool our real qubit to its ground state is the qubit with a virtual temperature beta v equaling plus infinity. So choose the virtual qubit with beta v plus infinity. And also assume that the norm of this virtual qubit is NV. So I'll remind you what norm is in a moment. So the idea is that that for a general case, which was discussed in a lecture, of swapping the real qubit with the virtual qubit, we assume that we take the virtual qubit between the levels I and j of the system, of the larger system V. And then we can write the state of this larger system V as just the state of the subspace to which we're restricting, and also the rest, which we label as rho V tilde. And here, then the norm of the virtual qubit that we choose between these levels I and j is just pi plus pj. And then the idea of the swap operation is that we treat these levels I and j as just, in the previous case, we treated the levels 0 and 1 of the second real qubit. So suppose that we have our real qubit S and our multidimensional system V, and then we have these two levels I and J. Oh, this is too thick. Yeah, and then the swap operation is analogously when we exchange 0j and 1i states. So this is SV, SV. Then if in a general case, the initial state of the system S is just PS 0 0 plus 1 minus PS 1 1, then the joint state of the systems S and V after the swap can be written as, so PS PI 0 0, 0I 0I, so this does not change. then for the state, the population of the state 0, 0j swaps with the population of the state 1i. And so here we end up with a population 1 minus ps pi for the state 0j, 0j, plus the second, which is ps pj for the state, ps pj for the state 1i, 1i, plus nothing changes for the state 1j, plus this additional residue from the rest of the subspaces of a larger system. So rho s tensor product rho v tilde. And then what we want to see is the partial trace. So what is the system? What is the state of the system S after we perform the swap? So we need to take a partial trace.
Sorry.
Yes.
Can you explain again what's this PV tilde?
So rho v. So essentially, here we're looking at the general case where we take a larger dimensional system. And this larger dimensional system V has a state rho V. But we don't want to use all of the Eigen States of the system, essentially. We only want to use these two, I and J, and kind of use it as a qubit.
It's just the remaining of the populations of all the states we're not interested
in. Exactly.
Okay, thank you.
You're welcome. Okay, so we want to see what is the state of the system S. So we just need to trace out the system V. And if we trace out the system V, then we arrive to the following. So I would maybe just at home advise you to repeat this operation by your own. But what we would get is the following. So we would get NV, the norm, PI over PI plus PJ 0, 0, plus PJ over PI plus PJ 1, 1, plus 1 minus NV PS 0, 0, plus 1 minus PS 1, 1. And here maybe just make a small comment again, comparing it to the case when we used not a virtual qubit, a second qubit not being virtual but being real. So for the case when the second qubit is real, you see that for the real qubits, this norm NV equals 1, because there are essentially only 2 levels for real qubits, and this residue matrix rho v tilde would be equal 0. And essentially in the case of the real qubit, indeed, the second term would just vanish and we will be left with the first term. Okay. But here we don't, and hence we don't achieve this perfect swapping that we do. Yeah.
Sorry again. Haven't we defined NV to be PI plus PJ?
Oh, yes, it's PI plus PJ.
And why are we writing it in this way and not just cancel out the terms?
Which terms would you want to cancel out?
If you go to the equation that you just wrote.
Yes.
We have the first term has NV multiplying and NV dividing.
Yes, so I wrote it in this way because, yeah, indeed, PI plus PJ is NV. You can write here NV, but I wrote this term in the brackets because it constitutes a valid density matrix. Moreover, it constitutes a thermal state for the temperature of the virtual qubit. So I'll just continue.
Okay, yeah.
Yeah, so then exactly following your question, then this can be also written as NV, thermal state at a temperature beta V, where beta V is the virtual temperature of a virtual qubit, plus 1 minus NV rho S. So this is why I took this NV term out. And so this is the state after an application, so after one application. And now we can write also the state after n applications. So to do so, we just make a following observation. So rho S prime minus Ts of beta V would be equal to 1 minus NV, rho S minus tau S of beta V. And so rho S prime can be also written as tau S of beta V plus 1 minus NV rho S minus tau S of beta V. And by induction, we can see that from this it follows that after we apply the same swap operation n times, which again, by this I mean that we don't use this, so we don't use the same virtual qubit, but we reset it to its initial state and then use it again. Or we just have a lot of copies, which we use. So then we end up with the following. And we see that if n goes to infinity, then the second term tends to 0, and we get closer and closer to the thermal state of the virtual qubit. Okay, and so coming back to our example, so in our example, the virtual qubit has temperature plus infinity, which means it's in a ground state. Sorry, its thermal state is a ground state. And then after n applications, we end up with the following. So maybe write it out. So 0, 0, S plus 1 minus NV to the power n. We start with the real qubit in a maximally mixed state. So 1/2 0, 0 plus 1/2 1, 1 minus 0, 0. And this is the state. Yeah, so it's this state. And here we see that, yeah, as I said, as n goes to infinity, 1 minus NV to the power n over 2 goes to 0, and rho S n goes closer and closer to the ground state. So repeating the swapping process each time with the resetted virtual qubit, we can cool our real qubit to the ground state as we wanted. So in the exercise sheet, you have to also calculate the energy change for each step of this process, for the cooling process, and also for the whole process. And as another example of where you would use the Qtrit as a system V, and so you would have you would be able to use two different virtual temperatures from that Qtrit to cool a qubit, and then see what is the optimal way of using these two virtual qubits of a Qtrit to cool down that real qubit. But generally, this procedure of cooling goes more or less the same, as in you apply the swapping procedure, you reset the system you're swapping with, and then you repeat the process again. There is a question in the chat. So I was wondering whether this cooling process is actually implemented in real life experiment. It's a good question. I actually would advise you to ask it to Rolf, because I know close to zero about experimental implementations of thermodynamics. Probably there was some implementation of this, I would expect, but I would advise you to ask Rolf. Okay, so this was about cooling. Then the second important part of the exercise is about composing virtual qubits. So the idea here is that in a lecture we've seen that we can compose two virtual qubits. In principle, of course, this can be extended to composing 3 qubits, 4 qubits, and yeah, how many virtual qubits you like. And then, for example, a question that would arise is, if you compose 2 virtual qubits, you know that you gain 2 more, 2 additional virtual qubits. How many would you gain if you compose 3, or if you compose n qubits? So for this, let us repeat again the process of composing them, and also see kind of the pattern behind it. So suppose that we have, I already say 3 systems, but first we'll briefly recap the case of 2, and then turn to having a third one also. So we have 3 systems, A, B, and C. And let's say that we use the following virtual qubits. So of the system A, we use these 2 levels, let's say. Of the system B, we use, I don't know, these 2. And of the system C, we use, I don't know, let me make it less spaced. These 2. And each virtual qubit has its own energy gap, which we label as delta EA, delta EB, delta EC. And also for just for convenience, we will label the states themselves, which we would use as 0 and 1s at the corresponding systems. So this is just a convenient relabeling not to mingle with this I's and J's. Okay, and then the corresponding energy levels. So the eigenvalues of this eigenstates, we'll just label them as A. So E0A, E1A, and the same for all three others. Sorry, for all two others. And also a parameter that we need to introduce here is the virtual temperature of each virtual qubit. So for the first, it will be beta VA. For the second one, beta VB. For the third one, beta VC. Okay, so suppose that now we have only qubits A and B. And for these two qubits, if we compose them, then we end up with the following Eigen States. So the first is 0, 0 on AB, and it has its energy is E0A plus E0B. The second eigenstate is 0, 1 with the energy E0A plus E1B. Then 1, 0, E1A plus E0B, and 1, 1. Okay, so now, in principle, to create a new virtual qubit, we would take, in this composite system, we would need to take a pair of any of these four states, right? The problem is that some of these pairs correspond to the virtual qubits that we already used, so they would be nothing new. So for example, if we take a pair 0, 0 and 0, 1, then we can just factor out the first system and we are left with the virtual qubit on the second system. So it's not new. The same argument goes for the pairs 0, 0 and 1, 0, where we can factor out the second system. For 0, 1 and 1, 1, and 1, 0 and 1, 1. So these are all not new, as in with the respect to the initial virtual qubits. However, if we take a pair 0, 0 and 1, 1, then this virtual qubit will be new. Just basically following our intuition that we cannot factor out any system, and essentially that will be a new virtual qubit with the energy gap delta EA plus delta EB, because to calculate that energy gap, we just need to calculate the difference between the eigenvalues corresponding to this eigenstate. So E1A plus E1B minus E0A plus E0B, which would give us just delta EA plus delta EB. And the second pair of states which would form a new virtual qubit would be the 0, 1 and 1, 0. So also be new. This would be a virtual qubit with the energy difference delta EB minus delta EA, because you would just need to subtract E0A plus E1B from E1A plus E0B. And so the one thing that you can notice about how these pairs of virtual states which give rise to new virtual qubits are constructed is that they are different. If you see the state as a bit string, then each bit in the state which is paired, which is a pair for example, the 0, 0 state, is different. So essentially, to create a new virtual qubit of using the state 0, 0, you just need to use a state which is for each bit in 0, 0 different from it. So you kind of need to negate this bit string. So hence we have the pair 0, 0 and 1, 1 and 0, 1 and 1, 0. This kind of guarantees that we cannot factor out any system and get a virtual qubit that we already had. And so let us now kind of use this intuition to see what happens for the case of 3 qubits. So for 3 qubits, we would have 2 to the power 3, 8 eigenstates. So we would have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Is it 8? Yes. I feel I'm back to my high school computer classes. But in any case, so we have this, we have these 8 eigenstates, and now we need to identify which pairs of them give rise to the new virtual qubits. And again, if we take a state 0, 0, 0, to find a new virtual qubit that we haven't already accounted for in the case for each combination of 2 virtual qubits that between these 3, we need to pair it with a state which is different at every bit. So we pair it with the state 1, 1, 1, just negating the string. So this would be one new virtual qubit. The next one would be for the state 0, 0, 1, it's 1, 1, 0. Then the state 0, 1, 0 has to be paired with 1, 0, 1. And the state 0, 1, 1 has to be paired with 1, 0, 0. So we get 4 new virtual qubits. So this intuition kind of gives us an idea of how many new virtual qubits we would have if we compose n virtual qubits. So for n virtual qubits, the eigenstates can be written as just a bit string containing n elements, right? If we label the states of the virtual qubits that we use in this composition as 0 and 1s. And then to form a new qubit, this bit string has to be paired with, I guess like this is not very strict way. So it has to be paired with its negation. So if S belongs to this set of bit strings of length n. So, which means that we can just take the set of this bit strings, which contains 2 to the power n elements, and for each member of this set, it has a unique other member, namely its negation, which gives rise to a new virtual qubit. So the number of virtual qubits would be exactly half of the number of states, because we can just divide them in these pairs. So we would have 2 to the power n minus 1 new virtual qubits. Okay. Maybe just a clarification, also as a remark. Also, by new virtual qubits, I mean that these are not the virtual qubits which gave rise, which n minus 1 system combining n minus 1 virtual qubits would give rise to, or n minus 2 or n minus 3. But these are the virtual qubits which are unique to the combination of n systems. It's the same as, for example, when we were considering these pairings for 3 qubits, then in principle, for example, if we consider the qubits 0, 0, 1 and 0, 1, 0, this would give rise to following virtual qubits. So the first system would just factor out, and we would have a virtual qubit between levels 0, 1, and 1, 0 for the qubits B and C, so for the last two. But this is something that we've already seen for the case of 2 qubits. So we're not interested in that. We're only interested in the things which are specific for the composition of 3 qubits in this case, which these two are not. Okay, so so in the exercise, you'll have to also characterize this case of composition of 3 qubits more thoroughly. In the same way it was done for the case of 2 qubits in the lecture. So in the lecture, also the virtual temperatures for these two new virtual qubits, which I think are labeled as beta V plus and beta V minus, were calculated. And here you would also need to calculate the virtual temperatures for each of these 4 new qubits, which is fairly easy. You just need to follow the definition. So I think this is all I wanted to say for today. Are there any questions?